So what we're doing here is we're taking an equation, we call it a function rule, where you're going to put in an input value for x and you're going to get out some number for y, and that's going to be an ordered pair. And we will be able to plot that, and we're going to do it multiple times. Now, we want to make a table of values that we can plot. And the question really is, what input values make sense? Now, this is just a standalone equation that doesn't have any real life situation attached to it. And so the fact is there's no real limitations on what you could plug in as a number, okay? It's possible to use any input x into the equation and get an output y. This suggests that if you choose integer values, you can produce output values that are integers as well, which means that when you graph it, it's going to be right on the grid lines, and it's easy versus decimal or fraction values. But yeah, there's going to be real life situations that limit it. In this case, we don't have limits on what the numbers could be. So we make a table, and they've happened to pick -1, 0, 1, and 2. So you can see that if this is the general equation and you put in -1 where x goes, and you calculate it out, you get 3. So the ordered pair input output is -1, comma 3. And you do it for 0, you put in 0 there, and you get out a 1. So 0, comma 1 is going to be plotted, 1, comma -1, 2, comma -3. And then when you plot that, you see these points there. And because there's no limit on what you can put in there, we can connect these. And what it means when we connect them is that numbers in between 0 and 1, for example, they're legitimate numbers to put in. You can put in anything, and it'll give you an output value. So you have a continuous line of all of the input values and what comes out. And the way you can look at a graph is you can say, at any point on the graph, like right here, what's down here was what you put in, and -1 in that case, right? Straight down is what you put in, and straight over here is what you get out, 3. So -1 in produces 3 out. So at any point, you could say, well, what would I put in and what would I get out? So here you would have put in -1/2, or you could have, and what would it produce? It would produce a 2. And you can try it. If you put in -1/2, -1/2 times -2 is +1, plus 1 is 2. So -1 produces a 2 out. And I know that because I go to -1 for the input and I follow it up until I get to the line, and then I just follow it over and see what the y was. And that will predict anything anywhere. Okay, if I put in 1/2, I go over to 1/2 for x, and if I follow it, in this case I have to go down to get to the line, and I go down, and once I hit the line, I say, what is that y value? And I go over here, it's -2. So if I put in -1.5, I'm sorry, if I put in +1.5, and I followed that to the line, I would see that it would tell me that a -2 would come out. Okay, so here is your got it problem. And what you're going to do is do what they did, make a table of values. What are you going to put in? Calculate what comes out so you have ordered pairs, and then you're going to graph it. Now, what this is saying is what I just referred to earlier. When you graph a real world function rule, meaning something that represents something in the real world, you want to choose appropriate intervals for the units on the axis, okay? Every interval on an axis should represent the same change in value, meaning if you go over the same distance every time, you should be increasing or decreasing the same amount, okay? If all the data values are non-negative, show only the first quadrant. And what that means is that you have 4 quadrants in a coordinate grid, and this is quadrant 1. And that's where you're going to have positive values for x and also positive values for y, okay? So if you only have non-negative numbers, you're going to use this quadrant here, quadrant 1. I like this problem. It's pretty cool. There's a function rule where W equals 146C plus 30,000. And what it represents is the total weight represented by W, what will come out. You'll be able to calculate out what the total weight is in pounds of a concrete mixer truck if it's carrying C, some input number of C cubic feet of concrete. And a cubic foot is 1 foot by 1 foot by 1 foot cube. Okay, that much concrete, apparently it weighs 146 pounds. And so that much concrete per pound times however many pounds are in there, plus an extra 30,000 for the weight of the truck, will give you the total weight. Okay, if the capacity of the truck, the maximum it can hold is 200 cubic feet, what's a reasonable graph for that function rule? Well, let's take a look. First thing it says is make a table to find ordered pairs that you can plot. And when you do that, we got to think about it essentially that the truck can hold anywhere from 0 cubic feet of concrete up to 200, that's its maximum. So those are values that you're going to pick. Those are reasonable input values. And when you put in each one of those values and calculate it out, you get these input values, meaning the lowest the truck could weigh would be 30,000 pounds if there was nothing in it, and up to 59,200 pounds if it was filled with 200 cubic feet of concrete, okay? And this says, how do you choose values for the real world independent variable over here? And you have to look at what's given to you and make sense. You can't go below 0, and you can't go above 200. So now you graph it. And these are ordered pairs, 0, 30,000. So what you need to do here is you'd say, if I had, let's say, up to 200, so the highest value is 200 here for the independent variable, how much concrete's in there, and the resulting output value would be how much total weight. Okay, so the total weight you can see the highest amount we're going to have is 59,200. So going up to 60,000 will make sure that it all fits in there. Now, the weight is never 0. The lowest it's going to be is 30,000 if the truck's empty. So when there's 0 pounds of concrete in there, or 0 cubic feet of concrete, I should say, then it weighs 30,000. And then with 50 cubic feet, it's going to weigh 37,300. That's up here. 100 cubic feet will be 44,600, etc. And you plot all of these ordered pairs. And since there can be any amount of concrete between 0 and 200, you can connect that with a solid line. And you can predict then any amount. What if we had, let's say 75 cubic feet of concrete? Then I would go over to 75 here and say, I'm going to follow it up until I get to the line. And that right there is where the line is. So if I followed that over to the y-axis, that would be about 40,000 pounds. Yeah. And you can use the graph to predict values that you didn't actually have by saying, what's in between the values that you did calculate. So you'll try it now with this got it problem. The function rule, W equals 8G plus 700, represents the total weight in pounds of a spa, like a hot tub you can imagine, that contains this many gallons of water, G gallons of water. And fun fact, water weighs about 8 pounds per gallon, and that's why there's an 8 there. Okay, so what's a reasonable graph of the function rule? If the capacity of the spa is 250, you can go from 0, no water in it, up to 250 gallons if it's full. Okay, so you're going to make a table of those values and graph them. And guess what? You're going to use graph paper. So get some graph paper. Don't meatball this and just draw out a handmade graph. We want to be using graph paper. Okay. Now also it asks you, what is the weight of the spa when empty? Explain. Now in problem 2, we could have any amount of concrete in there from 0 to 200, and it could be, it doesn't have to be whole numbers. It could be 27.3 cubic feet or 105 2/3 cubic feet, right? Any amount in between whole numbers. So you can connect the data points in a continuous line because any point between the data points has meaning. You could have that amount for any of them, okay? But some graphs might be composed of isolated points. An example that I often use is movie tickets. You can buy 1 movie ticket or 2 or 3, but you don't buy 2.5 movie tickets. So connecting them with a solid line would suggest that you can buy any amount between 2 and 3 movie tickets, and you can't. So you wouldn't put a connected line. You would put an isolated a set of isolated points, individual points. Okay. Now, this is what we call these. We call this a continuous graph if you can connect it and you go continuously along, versus discrete. Okay. There's 2 types of words for discrete. Okay. D-I-S-C-R-E-E-T means, can you be discreet? Can you keep a secret? Right? Discrete means keep it on the down low. But this is a different spelling and it's a different word. This discrete means composed of distinct isolated points, separated, not connected. All right, this is a real world problem. I actually really like this problem. Cheesemaker. A local cheesemaker is making cheddar cheese to sell at a farmer's market. And the amount of milk used to make the cheese and the price at which he sells the cheese are shown. Okay, it takes a gallon of milk to make 16 ounces of cheddar cheese, and each wheel of cheddar cheese costs $9. Okay, write a function for each situation, and then graph it. Is it continuous or discrete? Now, the situation is how much milk, how much cheese is made from how much milk, and how much money you can make from selling cheese wheels. Now, what this says here is how can you decide if a graph is continuous or discrete? And can you guess which ones are continuous or discrete here? Okay. Decide what values are reasonable for the independent variable. For example, if 3 and 4 make sense, do 3.3 and 3.7, some amount in between them, makes sense as well. So 1 gallon makes 16 ounces of cheese. 2 gallons would make 32 ounces of cheese. Does it make sense that you could use parts of a gallon? It does to me. Makes sense that you could put in any amount of milk between 0 and 1 gallon, or between 1 and 2 gallons, or anywhere, any amount of milk. Okay, but what about this one? So this one I would say would be continuous, because you can just pick any amount of milk and it'll produce some set amount of cheese according to how much milk you used. But cheese wheels, $9 each. You can sell 1 cheese wheel, you can sell 2, you can sell 3, you can sell 4. Can you sell 2.073 cheese wheels? Well, let's say that they're selling full wheels, and so no. Okay, let's take a look at this first one. It says the weight of cheese in ounces, 16 ounces for 1 gallon of milk, depends on the number of gallons of milk used. So the number of gallons of used milk used is independent, and the amount of cheese in ounces depends on how much milk you used. So the cheese produced is dependent on the amount of milk. Now, you can say 0 gallons of milk will make 0 ounces of cheese, 1 gallon will make 16, 2 will make 32, and you can plot these 0, 0, 1, 16, 2, 32, etc. But any amount of milk makes sense, so you can connect them. It's continuous. What about this one? Okay. The amount of money made from selling cheese depends on the number of n of cheese wheels sold. So A, amount of money, that's the variable they defined here, equals 9 times n, the number of cheese wheels sold. You sell 0, you get 0 money, $0. You sell 1, you get $9. You sell 2, you get $18. You sell 3, you get 27. You sell 4, you get 36. Okay, but he's only selling whole wheels of cheese, so it's discrete. You're either selling 0 or 1 or 2 or 3 or 4. You jump over the amounts between 0 and 1, and you don't connect them and plot points there. Make sense? Continuous versus discrete. So you're going to try your hand at this one now yourself, okay? You're going to graph each function rule and decide, is it continuous or discrete? And you're going to justify why you think it's one or the other. Justifying it means writing out in words, this is why I think this, okay? So here's the 2 situations. One, the amount of water W in a wading pool in gallons, how much water in gallons, depends on the amount of time, T, in minutes that it's been filling, as related by the function rule W equals 3T. And it kind of suggests that every minute, 3 gallons of water goes in. Here, the cost C for baseball tickets in dollars depends on the number N of tickets bought. And it's related by this function. The cost is equal to 16N, suggesting that each ticket N costs $16 because the units is dollars. Okay, so graph each one. Is it continuous or discrete? And explain why you know. So here you are. You are going to answer these problems, and by answering, you're going to be graphing by making a table of values and answering all of them. Um, some people are wise and are going to try these problems out genuinely to make sure that they have the practice and they have the concepts under control. If you don't do this, it could be because you don't feel like doing the hard work. And if that's the case, then don't be surprised if you're not going to do well with this. Um, I am going to urge you to actually attempt all of these so that you can pinpoint what areas you don't know how to do and you can follow up and ask questions. Anyway, good luck.